Hi, this is Kumar Singh. In today's episode of Throwback Thursday, we are going to go back further in time with a paper that can be undoubtedly, in my opinion at least, considered the most famous theoretical paper in the history of computing. The paper was on computable numbers, as you can see here, written by Alan Turing. It's basically a mathematical description of an imaginary computing device designed to replicate the mathematical state of mind and symbol manipulating abilities of a human designed computer. Turing conceived of a universal computing machine, right? So he thought of a universal machine as a means of answering one of the last three questions that was formulated by a mathematician, a famous mathematician of that time, David Hilbert, in 1928. Right? So the last three questions were: is mathematics complete? Is mathematics consistent? And is mathematics decidable? Hilbert's first question, known as, and I'm not sure if I'm pronouncing that right, but An-Chai-I-Jung's problem, concerns whether there exists a definite method, or, in the words of Turing's teacher Max Newman, a mechanical process that can be applied to any mathematical assertion and which is guaranteed to produce a correct decision as to whether that assertion is true. The Czech logician Kurt Gödel, I think that was his name, had already shown that arithmetic, and by extension mathematics, was both inconsistent and incomplete. Turing showed, by means of his universal machine, that mathematics was also undecidable. So to demonstrate this, Turing came up with the concept of computable numbers, which are numbers defined by some definite rule and thus calculable on the universal machine. So these computable numbers, which include every number that could be arrived at through arithmetic operations, finding roots of equations and using mathematical functions like sines and logarithms, every number that could possibly arise in computational mathematics. So Turing then showed that these computable numbers could give rise to uncomputable ones that could not be calculated using a definite rule, and that therefore there could be no mechanical process for solving all mathematical questions, since an uncomputable number was an example of an unsolvable problem. So from 1936 to 1938, Turing spent more than a year at Princeton University studying mathematical logic, right? And I think he was studying that with Alonzo Church, who was pursuing research in recursion theory. And it was Church who in August 1936 gave Turing idea for universal machine, which was later named as Turing machine. So the Turing machine, basically the gist of the core of this paper, the Turing machine or the universal machine, is a mathematical model of computation describing an abstract machine. Right? And that machine manipulates symbols on a strip of tape according to a table of rule. And that may seem like very simple, but despite the simplicity of this model, that machine is capable of implementing any computer algorithm actually, right? So an actual example from Turing's paper has been shown here. Now, if you go through this paper for the first time, I mean, I shouldn't say that you will also run into that challenge, but I at least ran into that it was challenging to follow initially because the logic is based around that machine, the Turing machine, which is based on a paper tape model, right? So the examples that you see here, right, are around symbols and their placement on the tape. So I had to go back to understand the basics of Turing machine, as well as I ended up studying some basics of magnetic tapes as well, the earlier form of data storage, right? But once you understand the basics, the paper becomes easy to follow, relatively easy to follow, right? So yeah, that is the fundamental core crux of the paper, the introduction of a computation machine which can solve arithmetical, mathematical algorithms, and that form the basis of the advanced models, somehow form the basis of advanced models that we see today. In fact, some believe that in 1937, after the paper, Turing and John von Neumann, right, has had their first discussion about computing and what would later be called AI or artificial intelligence. So to wrap it up, let's summarize why this paper was a significant milestone. First, it introduced the Turing machine, a simple abstract machine device that manipulates symbols on a tape, right? Yet it provides a formal model of computation, right? And it laid the groundwork for the concept of algorithm and modern computers. It defined computability. It solved the Entscheidungs problem, right? Because in this paper, he proved that there is no general algorithm to decide the truth of every mathematical statement. That is, some problems are simply undecidable. And it formed the foundation of theoretical computer science, like at least one of the elements of foundation, right? So to wrap it, Turing's work through this paper fundamentally changed our understanding of what machines and what math can and cannot do. It not only prefigured the development of modern digital computers that we use today, but it also established the limits of computation itself. In short, the paper defined what it means to compute and proved that not everything is computable. A revolutionary insight for logic, mathematics, and computer science. Thanks for watching.